Welcome back, Physics 30. So we're going to take a look at the section 26 here, the special theory of relativity, by looking at this preamble. So just to give you an outline of which parts we're going to be doing, we're going to be looking at Galilean Newtonian relativity, 26.2 postulates of the special theory of relativity, 26.3 simultaneity, 26.4 time dilation and the twin paradox, some really funky stuff there, and then 26.5 length contraction, and then we'll bring it home with 26.11 the impact of special relativity. So if we look over here, this little cartoon up here, a science fantasy book called Mr. Tompkins in Wonderland by physicist George Gamow. Imagine a world in which the speed of light was shortened down. So instead of being 3.00 times 10 to the 8 meters per second, it's shortened down to 10 meters per second, so we could see its effects in everyday life. Mr. Tompkins had studied relativity, and when he began speeding on a bicycle, he expected, as we'll see here, certain things happen. Weird things happen. One of them is length contraction. So he speculated that he would be immediately shortened and was very happy about it since he was increasing his figure. He wanted it to lose some weight, so hey, just travel at the speed of light, and that'll take care of everything. But to his surprise, however, nothing happened to him or his cycle. On the other hand, the picture around him completely changed. The streets grew shorter, the windows on the shops began to look like narrow slits, the policeman on the corner became extremely thin, and then he realized, oh my gosh, I see the trick now. This is where relativity comes in. So everything relative to him shortened in length, not him himself. But of course, to the policeman, if he was to look at him, he would see him shortened. So relativity does indeed predict that objects moving relative to us at high speed, close to the speed of light, or little c, are shortened in length. We don't notice it as Mr. Tompkins did because c is actually a very high number. We'll study a length contraction and time dilation and a couple of other things here. Okay, so that's kind of the preamble there. So if you look at the bottom here, the special theory of relativity, take a look at this question first of all. A rocket is heading away from Earth at a speed of 0.8 c, and what that of course means in physics, we instead of writing out 3.00 times 10 to the 8 meters per second, we just simply call it c. So we'll see this quite frequently. So 0.8 c, which will mean 0.8 times c, or 80% of what the speed of light is. So a rocket is traveling that fast away from Earth. Then that rocket fires a small payload at a speed of 0.7, 70% of that of c, aimed away from Earth, so in front of the rocket. So it's almost like this scenario back here, where we have a rocket, in this case a train, and then throwing something outside the train in front of it. Of course, back here with Galilean relativity, we saw that we add up the speeds and we get the grand finale, right? So, but what about light, though? What about traveling at an extremely high speed, that similar to light? Would you think the answer would be 1.5 c, a little bit less than 1.5 c? Of course, 1.5 is the magical number you get when you add these two. Is it a little over just the speed of light, a little under the speed of light, or 0.75 c? So what do you think right now? Maybe circle which one you think, and then we'll come back to that. Physics at the end of the 19th century looked back on a period of great progress. The theories developed over the preceding 3 centuries had been very successful in explaining a wide variety of natural phenomena. Newtonian mechanics beautifully explained the motion of objects on Earth and in the heavens. Furthermore, it formed the basis for successful treatments of fluids, wave motion, like you would have studied in Physical Science 20, and sound, which you also would have studied in Physical Science 20 as well. Kinetic theory explained the behavior of gases and other materials. Maxwell's theories of electromagnetism embodied all of electric and magnetic phenomena, and it predicted the existence of electromagnetic waves that would behave just like light. So light came to be thought of as an electromagnetic wave. Indeed, it seemed that the natural world, as seen through the eyes of a physicist, was very well explained. A few puzzles remained, but it was felt that these would soon be explained on principles we already know. Okay, so most of Physics 30 will be looking back on this, looking at Newtonian mechanics, looking at speeds that are far less than the speed of light, and Newton's laws hold true, and that type of relativity will hold true as well. But if we take a look, it did not turn out so simply. Instead, these puzzles were to be solved only by the introduction in the early part of the 20th century of two revolutionary new theories that changed our whole conception of nature, that being the theory of relativity, which we're studying here, and also quantum theory. And basically, this part is what MP1 is all about, Modern Physics Part 1. We're looking at these two things, and also we're looking at theory of relativity. That includes the special theory of relativity, which involves traveling close to the speed of light. It also involves general theory of relativity, which we'll look at gravitation. Physics, as it was known at the end of the 19th century, what we've covered up to now in this book, and what we'll be doing in Physics 30, is referred to as classical physics. So what we're studying in Physics 30, most of it will be that after this. The new physics that grew out of the Great Revolution at the turn of the 20th century, so i.e. when the 1900s started, is referred to as modern physics. So modern physics in a sense that it is 1900s. In this chapter we'll present the special theory of relativity, which was proposed by Albert Einstein, and then in chapter 27, the next part, we'll look at the quantum theory part of it. So we're going to start with the theory of relativity, the special and general theory, and then we'll look ahead to quantum mechanics. Okay, so that's the first part of the video here, just the introduction. In the next part, we'll look at 26.1 Galilean Newtonian relativity. Okay, so we'll see you soon.